researcher as well as an editor. As Ajay said, I'm at University of Delaware, Newark, in the United States of America. I came from India, so I'm very excited that this is an opportunity I've been given to connect with my fellow researchers in India. So hello, namaste. I will start first with my role as an editor. So I'm really fortunate that I've had the opportunity to serve as an associate editor for macromolecules. And now I'm also serving as a deputy editor for ACS Polymers Gold. I'll start there. I'll tell you about the journals first before I tell you about the exciting research that my students and postdocs do in my lab. So let's get started. Let me tell you about macromolecules and ACS Polymers Gold. So these are two out of, now there are 5 journals that focus on polymers within ACS. And so since I'm involved in these two, I'm telling you about these 2 journals. So you all know about macromolecules. It's been around for decades. It's one of the premier polymer journals. Actually, polymer journals, I should stop there, but I should also clarify it's from American Chemical Society. And so the editor-in-chief for macromolecules is Mark Hillmeyer from University of Minnesota. There are 15 associate editors currently for macromolecules, and I'm fortunate to be one of them. So if you submit to macromolecules, you may have me as one of your associate editors, or you may have one of my 14 other colleagues. In contrast to macromolecules, ACS Polymers Gold is new. It just was launched by ACS, and the AU is gold for a good reason. It's a gold open access journal, and ACS this year and late last year essentially launched journals. There were 9 thematic journals, gold open access journals. Polymers was one of the themes, hence this journal. And then there was also JAX Gold just before that. So these are overall at least 10 gold open access journals. And so for ACS Polymers Gold, the editorial team is myself, Deputy Editor Arati Jayaraman, and then as Associate Editor is my colleague Harmantan Clark from EPFL Switzerland. What I'm trying to do today in this first 6 to 7 minutes is to share with you information about macromolecules. Some of you may already know that. For the early career researchers here, this would be a way to learn about the journal. And then I'll also tell you about ACS Polymers Gold. What are all the similarities and what are the small differences? The differences, as I said, is about that gold open access. So I'll come to that. So first about macromolecules. I personally, as a researcher, publish in macromolecules a lot. So I view this as a very strong journal. Macromolecules, you know, publishes original, fundamental, impactful research in many aspects of polymer science. You may also know of biomacromolecules and ACS macro letters that emanated out of macromolecules. Biomacromolecules focuses a little bit more on the bio side of things. As the name suggests, ACS macro letters focuses more on rapid communication. So the letter format is what they go with. There are viewpoints as well there. So macromolecules has articles, has perspectives and reviews. The scope of macromolecules, and you can see the detailed scope online. So this is just some highlights. The interests include polymer synthesis, polymer phase behavior, polymer physics, polymer thermodynamics, self-assembly, order-disorder transitions, understanding structure and properties of polymers, as well as new characterization techniques, modeling, simulation, theory methods, and of course, like I said, take a look at the entire scope that's been presented online on the journal website. As editors, both Mark Hillmeyer as well as all of us associate editors, we're really striving to publish articles in macromolecules that showcase innovation, right? They showcase important and innovative concepts, new game-changing methods and experiments in theory simulations, and also have to demonstrate a fundamental advance in understanding of polymers. If your work is very applied, then the journal that you could go to, if you don't care about open access, then the journal you would go to would be ACS Applied Polymer Materials, led by my colleague Jody Lutkenhaus at Texas A&M. So that's about macromolecules. And so now I'll start to show you the similarities and differences. So I've already pointed to one thing, which is that ACS Polymers Gold is fully open access, gold open access, while macromolecules is a hybrid journal. What we mean by that is they have both articles that are under the subscription window, meaning there are articles that you can read if you had a, or your institution had a subscription. They also have open access. So some authors may say, I want to publish open access and I'm willing to pay the APCs. article publishing charges. And so then in that case, those articles alone you can read anywhere. You don't need to have the subscription. So it has both. ACS Polymers Gold is fully open access. What this means is every article that is published, every letter, article, perspective, review, so we have all those formats, everything that's published in ACS Polymers Gold is open access. So essentially anyone walking around on the road, in the bus, in a taxi can open their phone and read the article. They don't need a subscription. And the reason for opening such gold open access journals or launching them is because there are some grant agencies in some parts of the world which mandate that their researchers only publish in gold open access. And that type of a mandate is called Plan S philosophy. And so those researchers need a well-established journal where they can publish, where they know their work will be well recognized. At the same time, it'll satisfy that gold open access mandate. So that's why ACS launched these journals. So if you are supported by a grant like that and you need to publish gold open access, you can be assured that if you come to ACS Polymers Gold, you'll get the same, essentially, and I'll discuss that, same editorial experience or as an author experience as you would at Macromolecules, but it would satisfy the mandate. If you don't have that mandate, then it's your choice where you want to go. Would you like to go to Macromolecules? Would you like to ACS Polymers Gold? The author chooses. So a little bit more about ACS Polymers Gold, besides what I already just told you, which is that it's a fully open access complement of these journals. So in terms of scope itself, it essentially encompasses the scope of macromolecules, macro letters, biomac, and applied polymer materials. Expectations, review standards, are expectations of quality and impact are the same as that you would find in macro letters, macromolecules, biomac, or applied polymer materials. And the way we establish that equal editorial task, whether it's macromolecules or ACS Polymers Gold, is through this dual editorship. So while I told you I am an associate editor at Macromolecules and ACS Polymers Gold deputy editor, my colleague Harmantan Clark, like me, is also concurrently an associate editor for Biomac and ACS associate editor for ACS Polymers Gold. So by doing that, we know that we will treat the papers the same whether they came to Polymers Gold or Macromolecules. So that's a little bit about ACS Polymers Gold. Because it's new, I thought this was important. What have we been up to in the last 6 months? We've done a few things. And so if you want to learn a little bit more about our philosophy, the reason for this journal to exist, what is this open access? If you're a young researcher, you may not yet know. Check out our inaugural editorial. It's written by both of us, myself and my colleague Harmantan Clark. It's in the first issue of ACS Polymers Gold. And then I also want to point out that we have a diverse advisory board. These are researchers from around the world. We have representation from India as well. And we had a very successful first advisory board meeting where we were given good advice and guidelines from these researchers. Each of these researchers comes from a different continent, country, research area, and they realize that they have different needs. So it's good for us to understand the different needs and at the same time, different limitations that folks may have. So this, you can take a look as well. It's on our website. Our first issue was published in August. And in this particular issue, we had articles and letters. But as I said, we also have perspectives and reviews, and you'll see that in the next issue. The topics, like I said, pretty much demonstrate the scope I described earlier: polymer physics, simulation, synthesis, mechanochemistry, measurement techniques, biomaterials. And this is one of the covers of one of the authors that we highlighted as a 2021 Rising Star. So you'll see more such young researchers being highlighted, and there'll be folks from India too that will soon be highlighted. And so you can also see other articles that have been accepted that are in ASAP status right now, and you'll see the different formats of articles as well as the different themes. So you can take a look at this online. And the last thing I want to share is that this is an open access journal. Now in Macromolecules, if you have a subscription, you submit for free, but of course you can only read if you have a subscription. Open access means you can read anywhere, anybody can read, but to publish, you need to submit article publishing charges. These are more the general charges you will see online, but relevant to my colleagues, you all in India, it's a reduced, a discounted APC price, and it ranges from $350 to $550, depending on the type of copyright license you choose. You can also extend talk to your institutions to do read and publish agreements, perhaps. That's like extending subscriptions. So you can, the cost of publishing open access doesn't fall on the authors, and it can fall on the institution. So you can take a look at that. Again, I'm not the right person for that. I'm playing the role of an editor, but these are, this is information available on ECS website. So that was about my role as an editor. And how I am involved with American Chemical Society. Now I'll switch hats, and now I'll become the researcher and author like you all. And so now I'm going to share with you the research that we do in my group at University of Delaware, Newark. So my group's focus is on polymers, obviously, as you guessed. But in particular, we are focusing more on computational studies of polymeric materials and soft materials in general. My group's focus is, in terms of philosophy, is always to link what is happening at the molecular level to something macroscopic. So that could be structure, that could be thermodynamics. And this philosophy we extend to a variety of projects. You can see this here in the top corner. We are interested in polymer functionalized particles. I'll actually discuss one little story from here today. So our focus there is on the design of the polymer on the particle to tune how the particles behave. So there again, the hero is the polymers. And then we also have work in my group on polymer blends and solutions. And I'll show you one little snippet from here today, because that's related to a computational tool we developed for our experimental collaborators. I'm very fortunate in all of these projects. I have amazing collaborators who do experiments to help us validate what we study computationally. So you'll see a bit of that there. What I don't get to share with you today is the lower half, which is the biomaterial side. So we do work on polymers, peptides. We've worked with nucleic acids. We're now working with polysaccharides. So essentially bio-inspired, bio-derived, biocompatible materials. Everything is macromolecular. So we focus on model development and studies, design of these materials for a variety of biomedical applications. I won't get to talk about that today. So all of that science that we study, like I said, is using, in my group, is using molecular models, simulations, and data science techniques. Using a combination of these various methods, we are focused on obtaining deeper fundamental understanding of soft materials. And I'll share one story of the many stories today to share that with you. We also work, like I said, with our experimental collaborators, so we can use that understanding to design and engineer new materials with improved properties. I don't share that part here, but I'm happy to talk with you offline another time. We also, in the process of our collaboration, sometimes realize we can develop good computational tools that our collaborators can use to better analyze structure. And so I'll share that one snippet today as well for those of you who may be interested on that side. So let's get started with the first story, the obtaining deeper fundamental understanding. And so this particular little story falls under the big umbrella in my group of studying macromolecules and macromolecular materials with directional interactions. So those of you who may be more familiar with biochemistry and molecules in biochemistry, like proteins and DNA, you know directional interactions like hydrogen bonding, pi-pi stacking, really are found universally in these materials. Secondary, tertiary structures are stabilized because of some of these interactions, in addition to other isotropic, I would say, interactions, effective interactions. In synthetic polymers also, you can bring in beautiful valency and program valency into the structure because of localized hydrogen bonding or pi-pi stacking. On top of that, you can also tune the thermodynamics and say, I can make a material that's thermoresponsive. So at low temperatures, it does one thing. At high temperatures, it does a different thing because the hydrogen bonds are stabilized at low temperatures, break up, and entropy dominates at high temperatures. So that's another beauty that comes in because of directional interaction. So this really was motivating us, because in many of the systems we started studying, we realized directional interactions and macromolecular behavior was important. And we realized atomistic simulations where every atom is shown explicitly wasn't going to work when we're dealing with macromolecules and localized hydrogen bonding. You may get the localized hydrogen bonding really well with atomistic simulations, but polymer movement, rearrangement, that time scale is huge in the atomistic world. So we had to develop new coarse grain models. I'll share that story today of how we used that new coarse grain model in one particular study. But we started off this journey of developing such coarse grain models for macromolecules. What that means is a little less detail than atomistic, but holding on to the important information you care about. So coarse grain models for macromolecules with directional interactions. It started off actually in the nucleic acid world, and then we moved over to generic polymers. I'll share this story today with you in the nanocomposite world. But like I said, we've been interested in biomaterials and bio-derived materials, and we can't escape hydrogen bonding and directional interactions there. So we've developed some coarse-grained models in that era, in that particular area, in the current era, in that particular area. Again, I don't get to share that, but you can see these papers on our website if you're interested. My focus is on polymer composites, to tell you that one story today. So this is our focus, right? We want to be able to study polymer nanocomposites where there's hydrogen bonding chemistries in the polymers. In particular, you'll see as I go forward that we're interested in systems where particles are functionalized with polymers and then placed in a free polymer. So the green here would be the free or the matrix polymer, and the blue would be the graft polymer, right? So this is work from one of my collaborators' lab, Ryan Hayward. He used to be at UMass Amherst, now at Colorado Boulder. They had shown that hydrogen bonding chemistry between the matrix polymer and the graft polymer allowed them to create a thermoreversible polymer composite. So this is something we'd like to study and come up with cool designs and how we can make it so we can tune the thermoreversibility, tune the phase behavior. So for that, we have to, like I said, we needed new coarse-grained models that could handle the polymer length scales and time scales and have directionality programmed in. So that's basically what I'll show you today, how we've used simulations to conduct fundamental studies. Before I get to that, let me just give you a few background pieces of information that are important so you can appreciate some of the results we've got. So in this field of polymer composites, people are trying to control where the nanoscale fillers, nanoparticles, go within the polymer matrix. And if you had just bare particles, getting the particles to disperse in the matrix is often a challenge. And we know you have to achieve these different morphologies for different properties, right? If you want certain types of conducting properties, you need a certain morphology, mechanical properties, a certain morphology. So controlling where the particle goes and the morphology of the composite is important. So one way people have been tuning or controlling the particle dispersion aggregation is through grafting of polymers on particles. And so they can choose the chemistry of the polymer on the particle, and then basically by the design of these graft chemistries and matrix chemistries, they can tune where the particle goes, especially at high grafting density. So what I mean by that is, imagine this particle is completely densely grafted with polymers. You've essentially covered the particle surface and screened the particle-based interactions, and everything is really controlled by the polymers on it and how that interacts with the polymer around it, the matrix. So at this high grafting density, if you choose the chemistries to be the same, then essentially, because everything is densely grafted on the particle, the net morphology is driven by entropic driving forces. And of course, if the chemistries were different and you want that, then in that case, you're now dialing in enthalpy as well, and how those two chemistries talk to each other plus entropy together dictate whether you're going to get dispersion or aggregation. So I'll be in this second bullet, but I'm going to tell you a little bit about the previous bullet as to the important entropic driving forces, because that doesn't disappear in the second. It's just there along with enthalpy. So at this point, I want to share some stories that we have worked on. There are other groups in the community that have also worked on this problem, but I wanted to highlight two stories that we had published in this area using a combination of theory and simulations. I don't get a chance to tell you about the theory itself today, but I can guide you to a reference if you're interested in the method. But what we found is when the chemistries are the same in the graft and the matrix, and you have high grafting density, the way to tune those entropic driving forces to favor dispersion is by choosing molecular weights such that the graft is a really large molecular weight and matrix is small. So then the mixing entropy of the matrix penetrating the graft layer is dominant, and the conformational entropy loss of the matrix upon entering the grafted layer is small. So it basically wants the two to mix, particles and matrix mixed, you get dispersion. And we found that we can also favor dispersion and tune the entropy towards that by increasing polydispersity or dispersity of graft chain molecular weights in a matrix that is not so polydispersed, not so dispersed in molecular weight. And we showed that using calculations with prism theory and MD simulations, and that's shown here, that two particles' effective interactions in the matrix goes from being attractive at the monodisperse level to becoming purely repulsive as you dial in dispersity in molecular weights. And that's again goes back to some terms that are increasing that mixing entropy gain, driving it to dispersion. We also found that changing stiffness, making things stiffer. So if you chose polymers with higher persistence lengths, you would favor dispersion more than lower persistence length. And similarly, particle curvature, if you chose smaller curvature, then you have higher chance for dispersion. That was all entropy. As I said, our goal is enthalpy and entropy. So what happens when you bring in different chemistries? And so this was not so long ago, we had published a paper with Professor Ramanan Krishnamurthy doing experiments at Houston that showed that if you chose different chemistries that have enthalpic attractions, right? So these chemistries are LCST-like phase behavior chemistries. So at low temperatures, they love to mix, and at high temperatures, they demix. So that graphed matrix phase behavior dominates this morphology of the composites, where at low temperatures, so this is reduced temperature in simulation units, but the experiments confirmed this as well in that paper. Low temperatures, the matrix is happy to wet the grafted layer, mixing with the grafted layer. That's what the y-axis is telling you. And at high temperatures, the demixing of the graft and the matrix causes demixing of the particle and the polymer and the matrix polymer, and leads to aggregation. The difference, the important thing that we found was that these two are not just identical transitions. Wetting to dewetting, wetting to dewetting is continuous, while dispersion to aggregation was a first order transition. So that's just a little bit extra physics there. And so, like I said, our goal here is to see directional interactions and what that does, right? So these were all isotropic attractions. So our goal is to compare isotropic versus directional. Is there something that's unique when there's directional interactions and how things wet, de-wet, and dispersion and aggregation? That's the story I'm trying to share with you today. So for that, like I said, there was a need for a coarse grain model. I'm going to do great injustice to my student Arjita's work here by just putting together everything she did over months in like a minute of a slide. But please take a look at the details in this macromolecules paper of what we've done here. This is a phenomenological coarse grain model where we are bringing about the effect of that directionality that one may see in hydrogen bonding through this coarse grain model. So we do that through the choice of these light, small beads, which we call sticky beads, ghost beads that sit mostly within the monomer beads. And that little exposure of that sticky bead is what gives that attraction, that directionality. It's a tiny volume where that attraction is felt. So the choice of attraction strength, the size of the beads, where they are placed, what bonded interactions they should have, how restricted should they be along the backbone, all of that together give the net effect that looks like they are directionally interacting. At the same time, you still have isotropic interactions between the backbone graft and matrix beads. So you can also isolate the two and study fundamental deeper questions because of this model. Okay, so we get directional, we're able to mimic directional interactions through this. And so let's now get into the science. We want to know what happens for isotropic versus directional in terms of wetting. So here I'm showing you a profile which is called monomer concentration profiles. As we go away from the surface of the particle, how do the graft monomers arrange? How do the matrix monomers arrange? Graft monomers arrange, matrix monomers arrange. You see the graft has a certain profile dense near the surface. As the volume of the shell increases, you are dividing by a bigger number, so small values of the concentration. Matrix is penetrating the grafted layer. You can see that there's overlap. That was at the purely entropic limit, black line. Now let's look at the pink or the purple line. This is what happens when you now incorporate directional interactions between the graft and the matrix through those little sticky beads. You see that the grafted layer is now stretched out, right? It's going farther and the matrix is going further in. And so there's increased wetting. What if you did this isotropically? So if we had incorporated isotropic attractions, now, of course, here I'm using a model chi parameter. These are basically increasing attraction strength between the graft and the matrix beads isotropically. So these values will be much smaller in KT compared to this, because this is very small volume, very strong. This is small attraction isotropic, but you can accomplish same wetting. So it doesn't matter what type of chemistry you choose, you can accomplish the same wetting, right? And so this is important for many reasons, because wetting, de-wetting, like I said, is related to dispersion aggregation. But there are some unique differences between the two types of interactions, and that's at the chain level. So if you see each grafted chain, in the case of directional interaction, only interacts with a few matrix chains as compared to the isotropic, where it interacts with many more. Furthermore, the free volume per graft chain, so this is important in thermomechanical properties, that distribution is lower, so everything's tighter in the case of the directional interactions compared to isotropic. So while wetting may be the same, the chains themselves slightly are behaving differently. And so the thermomechanical properties and rheological properties could be different, even if the equilibrium wetting is the same. So that's important to see. So the next question is, what happens to dispersion? What happens to aggregation? Are they going to be the same? So I'll tell you really quick that the behavior we saw for directional versus isotropic at the particle level dispersion aggregation is the same. But we found something very cool, and that's what I want to share here today. So I will no longer distinguish isotropic to directional, but I will tell you what happens as you increase that attraction, whether it's isotropic or directional, it doesn't matter. Attraction between the graft and the matrix. So here I want to point out something we do with theory and simulations. When we work with these systems, as you can see here, these are very large simulations. And that means we have to give it enough time and make sure things are not trapped. And so to ensure that our results are not just a kinetically trapped garbage, we need to compare it to another method that may have different approximations, but not the same one as simulation. So prism theory is one way where we are solving analytical equations or integral equations, but numerically or analytically. In this case, it's numerically. And do we get the same answer for the same model? So that's why I'll always show you simulation and theory next to each other here. And you'll see that the behavior will be mimicked in both, which gives us confidence, right? Also, the theory answers come really fast compared to the simulation answers, but we obviously have no visuals in theory, so it's nice to have both. So this is at that entropic limit. You already saw this plot. So now let's make it more attractive. And you see, as you make it more attractive, something opposite to your intuition is happening. I told you before, when things wet, particles want to disperse more. But now I'm seeing that the particle-particle correlation has a higher peak. So there's more correlation among the particles, but at larger distances. So keep that in mind. A little bit more attraction, you get the same. And this is not a function of simulation or theory. You're getting the same trend in both methods. So why is that? So here was our hypothesis, and I'll show you how we proved it. Essentially, what we found is that the grafted particles, when the matrix is wetting it, so you see the matrix chains are inside, you remember that the concentration profile expanded. So the grafted layer that is like this, when the matrix is penetrating it, it expands to fill in a lot of matrix. So it becomes larger and harder. So we think that the increased wetting leads to that increase in size and hardening. And then they end up acting effectively like hard spheres instead of the soft, hairy particles. And then those hard spheres and these tiny polymer chains around them essentially act like a system of colloids and tiny polymers and expect to see depletion attraction and higher particle correlation at higher distances. So that's what we wanted to prove. So here we went even more coarse-grained, right? Where each bead is not a polymer, but the whole polymer is represented with some spheres. And so now we have the whole polymer matrix with a sphere, coarse-grained. The whole grafted particle is also one sphere. But the way we model these spheres is to reflect what we just want to test, which is less wet, so small and soft, more wet, large and hard in a matrix. What do we see? So essentially at that entropic limit, they should essentially be dispersed because they should be soft and less wet and small. And at the higher attraction, they should be large, hard, and they should demonstrate that you get higher pair correlation. So do we see that? Indeed, we see that. With the very coarse-grained simulation, you can see these images here. These were the radial distribution functions, particle-particle correlations we see that mimics what we saw earlier, proving our hypothesis. So this is one of those fundamental stories. The reason I chose this is to show you how we combine theory and simulations. And sometimes different levels of coarse graining, and how we also use a directional interaction, a phenomenological coarse grain model. And so this to me felt like a story where I could demonstrate all of those things that we do to different extents in our different studies. And that's why I shared this with you. So I want to summarize this part before I move to the second part. So I wanted to show you a coarse grain model that we developed. That phenomenological coarse grain model mimics obviously a large polymer behavior because it's a long chain and localized directional interactions. And we found that if you use that type of chemistry in composites, you can get similar wetting, matrix graft wetting for the directional and isotropic. But even if it's equivalent, your chain level contacts and free volume is different for the directional and isotropic. They both lead to increased pair correlation functions between particles. And in that, as you increase the attraction strength, and that's because you have more wetting, particles get larger and harder and essentially show higher correlation because of depletion-like effects. And so this was funded by Department of Energy, and I want to highlight that this story was one of many chapters that Arjita is writing in her PhD thesis, and she's a 5th-year student, and she's also originally from India. So now I want to shift gears in the next 10 minutes I have, 10 to 12 minutes, towards this next little tidbit I want to share with you. So I've told you how much I truly enjoy working with my collaborators, and I've learned a lot from them. My experimental collaborators allow us to have realism in our work. At the same time, they're also teaching us how to communicate with them. And oftentimes theory simulation folks and experimental folks can talk a different language. So we've learned a lot. And in that process, we ended up developing a method that I want to share with you today. And in fact, just yesterday, we released the software package and taught a tutorial on this method. So this is kind of exciting to me. So let me motivate you on why we needed this method at all. So most of my collaborators who look at structure in polymer solutions or polymer composites use small angle scattering. And they go to places like NIST, National Institute of Standards and Technology, or Brookhaven National Lab or Argonne National Lab to do these experiments. And so when they do neutron scattering or X-ray scattering, they are basically, for a given solution or composite or film, obtaining profiles of scattered profiles that look like this. So these are intensity curves versus wave vectors. And then basically they have to figure out what this means. And so how they do that is they say, oh, I think I know what is in the solution. And so let me go find an analytical model that will be good representation for this structure, fit that analytical model, and then get the parameters out. So those analytical models could have radius of gyration squared average or size of the particle, etc. Right? But these analytical models have approximations. They work pretty well when your structure is a good conventional structure, the polymer is pretty standard. But these days, we don't work with standard polymers or conventional structures because of our awesome experimental collaborators who synthesize amazing polymers and have amazing techniques to create structures that don't have analytical models. So what do you do in these cases where those analytical models either are too approximate or they just don't even exist for the structure you're looking at? How do you then interpret the scattering profile? So this is why we wanted to come up with a computational method that allowed us to analyze these scattering results and not have to depend on analytical, off-the-shelf analytical models. So that's where our method came in. We call our method CREASE, Computational Reverse Engineering of the Scattering Experiments. So CREASE, and the main idea is it's made of 2 steps. First step is basically the solution's scattering profile, the intensity versus wave vector the experimentalist got is sent as an input. And the first step is a genetic algorithm that takes that input and then determines the structure, relevant dimensions of that structure. So here the example is of a vesicle with 3 layers of wall. And those dimensions are usually what people want to know. How big is my structure? What is the inner features in that structure? That's usually what people want to know. And then beyond that, people also want to know how those chain molecules that were in the solutions are packed within these structures. And so then we take those dimensions and in the second step, reconstruct the molecular level detail and show chains, how they pack and how they arrange and the size distribution, etc. So I'll give you a brief overview of the algorithm, and then I'll show you 3 applications that we've had of this. And of course, the references if you're interested in reading more. So the main idea is we're using genetic algorithm. What this is an optimization technique. It's been around for many, many decades, but we've applied it here to this problem, and this is the first time for this problem. We start with a bunch of individuals that look like the shapes that the experimentalists are seeing in microscopy, say. So they think it's spherical, it's cylindrical, it's vesicle-like. So we work with those candidates. The only other inputs the experimentalists are providing to the genetic algorithm is obviously the IFQ versus Q, which they've observed from the scattering, and everything they know about the solution. What's the polymer, what's the solvent, what's the concentration, etc. So you obviously know what you've put in. So we start with a set of individual structures with varying dimensions for that shape. And then basically in that shape, we then place scatterers. So there's no chains here at this point. So there's no approximation of any chains. It's just a bunch of scatterers that we throw in various regions. We identify them by 2 different chemistries. So if it's solvophilic, solvophobic, we basically say, okay, blue and red, one for solvophilic, one for solvophobic. Then we calculate the I of Q, computed I of Q for that structure. And we do this for obviously every individual that's in that population. So large population means you have a diverse set of individuals you're going to select from and eventually find the individual whose computed I of Q matches the experimental I of Q. That's what you want. And then you know those dimensions of that structure, you have your answer, right? So for all these individuals, we calculate ICOMP, then we calculate fitness of that individual, and we do that for every individual. Fitness is basically how closely does the comp I of Q match the experimental I of Q, right? So higher fitness is a good thing. You want to get to the individual which has the highest fitness. That's the best individual whose computed I of Q matches experimental I of Q. If the fitness is converged, give us the answer. If it's not, go back. And from that population of individuals, select the next set of individuals for the next generation that basically are getting better and better in fitness, right? And so you will select, or sometimes bring in diversity by mutating a few, or sometimes you just do crossover. Two parent individuals create an offspring. Regardless, you just get your next generation. You do the same cycle, next generation, next generation. Over time, the fitness will start to converge to high value, and you'll start getting the individual whose computed I of Q matches the experimental I of Q. And then you can get the output that you care about. So the output could be dimensions, it could be something else. Like in this case, we were also interested in aggregation number when it was a spherical micelle. In vesicles, we didn't care about the aggregation number. We wanted the individual dimensions only. So it depends on the parameters you want to get about that individual. So there you go. This is basically what we did. So then the second part is the molecular reconstruction. So some may say, I'd like to know how chains pack in this. So you can choose the type of model you want to choose. You can then fit that model into the structure you just got from step one. The dimensions were what came out of that first step. And relax the chains, let them equilibrate, and then you can get a lot of chain level information. Things that you won't get, like distribution of chain conformations. No analytical model is going to give you that unless you develop it from scratch. And then you can get concentration profiles. How mixed or demixed are the two domains? Is the interface rough or smooth? You can see that in the concentration profile. It's a lot of information that you want to get for that structure beyond analytical models, even if you had a good analytical model. So these are the two main steps. So I will not obviously give you every story we've created with this method, but just give you highlights so you can appreciate its application. So we've applied this to first the simplest case, spherical micelle. That's why all the diagrams were like that. Then we went on to aspherical structures, all because our experimental collaborators were seeing structures that didn't make, that the analytical model couldn't do a good job of, you will see. And then we did some machine learning enhancement. I'll briefly describe that in the end. And then vesicle structures as well. I won't talk at all today about this part, which is actually also figuring out how particles pack, not within a vesicle or a micelle, but in a solution of mixtures of nanoparticles. We've also done that. So let me give you the first example of how things looked in the spherical micelle world. This was experiments starting from synthesis in Karen Woolley's group at Texas A&M. She's also a JAX editor, so you may have interacted with her. Her student synthesized the polymers. Darren Pochan at UD, his student did scattering experiments and did the analytical model fits in microscopy. We knew we were getting spherical micelles, and so we basically used the crease code for spherical micelles. What we saw is the dimension of the core, so that's that red region, matches in from crease, analytical model fit in SAS view, microscopy, cryo-TEM. All agree really well. But you will see that the analytical model fit does not agree in the micelle diameter with cryo-TEM at all. It doesn't fit at all. And so then when, that's the wrong direction. Let's go this way. If you look at crease, now the numbers start to get closer and closer to cryo-TEM. The radius of gyration that we got from the second step, that also agrees really well. If you take the micelle diameter and the core diameter, how big could the chains be in the corona? That is in good agreement as well. And so is the aggregation number that you can back calculate from the density. The reason probably the analytical model didn't do super well is these are very complex polysaccharide backbones, charged side groups. Likely the analytical model was not taking the statistics of the chain conformations right, and thus over predicting some of the micelle diameter. And that's why it failed. And that's why crease is a good method to work with. Similarly, we did the same, but in this case, now we moved to cylinders, and cylinders now, this is an in silico experiment, so we know the right answer already. And so we tested that with crease. So here are cylinders with dispersed dimensions. And when we applied crease, our dimensions for the cylinders are within the standard deviation of the in silico cylinder diameter and core diameter. So this is answers we knew in this case because it was an in silico experiment. The reason we did that is we wanted to show you that the molecular reconstruction agrees really well. So when we reconstruct using purely these dimensions, do we get back these conformations that we had there? And we do. So the radius of gyration of the red block and the blue block, the distributions from our reconstruction and the original experiment agree. So that's why we do such experiments, to know that. We use our own scattering data from our simulated experiment. So in the last few minutes, I will wrap this up, but I want to show you a couple of examples. One is vesicles, and then one is how we improve things with machine learning. So in vesicles, in our collaborator Christy Kick's lab at University of Delaware, we've seen vesicles in her microscopy images. They are pretty dispersed in sizes, right? So we basically said, let's take the hardest case of a solution with very dispersed vesicle diameters. And here we know the right answer, just like in the previous slide. Do we get these answers back? And do we do better than an analytical model fit? So clearly, this is how noisy the the scattering looks from this in silico experiment. This is how things look as the genetic algorithm progresses from low generations to high, how it fits. And then from that, we get the dimensions at the end of it. And you can see this is the core diameter, the inner layer thickness, blue layer and red layer thickness, that's TB, next layer thickness, that's TA out, and then the sum of all of that. So now you can see that the target values from our original experiment is in black, and our genetic algorithm in dispersed and without dispersed is in the color. We can handle dispersity really well in genetic algorithm. It also tells us how much dispersity we have. You can see it gets pretty good agreement. But if we now see the SAS view fits with a good analytical model for vesicles, it does a poor job in many of the dimensions. And so in this particular case, dispersed vesicles is handled much better by CREASE than if you had a good analytical model for vesicles and used a nice fitting package that many scatterers use. So the last piece of information I want to share with you, I'm going to go to this part, is how we've used machine learning to make this method better. So far, I've pretty much sold the case that this method's really good. But the part I didn't tell you is that it's very slow if you just did it the way we did it. And that's because in the scatterers that are placed, and when we calculate the computed IFQ, that calculation is very heavy. There's lots of pairwise distances and then multiple individuals, multiple generations. It's very slow. So if we could have a machine learning model that takes the dimensions of that structure, say in this case, it's the diameter of the core, the thickness of the corona, the length of the cylinder, it could be different for the vesicles. And then that machine learning model directly converts it to an IComp of Q. You're not doing any of these calculations. It's super fast then. So we did do that. And so this was work, last chapter of one of my other students' thesis. What we found is that compared to the original genetic algorithm, which is in blue, this is the sum of squared errors. The lower this is, the fitness is high, and the faster it converges, fitness converges fast, we get an answer fast. So you notice that the blue has this behavior over generations. This new cycle is similar to the original with the difference that every generation we train a neural network model and use that to quickly calculate IComp, suggest a candidate, send it back to the main. So the main is still slow, but this side is very fast. And the side suggestion apparently makes a huge difference. This quick side calculation with the machine learning allows us to converge to answers fast. Not only fast in fewer generations, but also if we just wanted to use that side cycle, that has much faster speeds of calculation than if you ran one generation of this original genetic algorithm or this combined loop. So if you invested time in developing a really good machine learning model, you can just use that and run just this pink cycle and you'd get answers really fast. So that's something we are suggesting to our scattering colleagues at NIST, and that's why we ran the symposium yesterday with folks at NIST who manage scattering. And so this is the open source package that we've released. If you're interested, you can take a look during question and answer. I can keep this open if you want to take a look at it, or you can reach me and I'm happy to share that. I'm going to end my talk here so that there's time left for questions. I want to acknowledge the people who did the work. As I said, Arjita was the one for the polymer composites work. My students, DJ Wu, Christian Heil, Mikhail, postdocs, all contributed to the development of CRIS, which I shared with you, and then, of course, funding and supercomputing. And thank you for your time and attention.